Good morning, everyone. Thank you so much for waking up so early and coming here, taking into account that the weather outside is actually makes it perfect sleep, so I totally appreciate this. My name is Olena. I work for Confluent. Confluent was founded by the original creators of Apache Kafka. And we do a lot of real-time data streaming, data processing, analytics, and we take security very, very seriously. So today I wanted to share with you some learnings which we have and some ideas for you if you run similar systems, what you can do to protect those systems in various different situations. And starting with actually data streaming and how data streaming changed over the past years. Take, for example, a financial institution, and we no longer have it as a big isolated system anymore. It has to communicate with a lot of other systems inside and outside of it. So it creates this kind of like a web connections where the data is sent across. So whenever you are making a payment somewhere, that transactions goes to the system, it has to be processed very quickly. And the whole system is like we know that we can catch all those events and we can process them fast, but the question is, can we process them fast enough to make those quick decisions based on the information which we are getting before the data becomes stale or risky to ignore, like in different examples, for example, fraud detection systems. So the whole system which we have is quite powerful, but also it is quite messy. So we are dealing with huge volumes of data. We need to move it at high speeds, and we can have all sorts and all kinds of data. Some have higher security thresholds, some are less risky. The system has to scale very fast. It has to adapt to the changes and new features without introducing any vulnerabilities. So there is a lot to happen here. And yeah, and what can actually go wrong when you are dealing with all those complexities? Which brings me to the next chapter of my talk, which I called Security Bloopers Awards. So here, a couple of cases where things went wrong. And the first award goes to a company in Brazil, and I call this award Who Needs Authentication Anyway? Because actually, they built a very sophisticated chatbot, which probably brought a lot of useful features to the users who could ask their questions about the health concerns. It was a health company. It is a health company still. But they forgot one tiny, tiny detail, probably, in their opinion, less important, to put authentication on the Kafka broker. So anyone who could access Kafka broker from outside and read all the data which was coming from the chatbot, all those awkward conversations about health concerns, and while the team which uncovered the attack, they caught over 100K messages, but they also estimated, based on the logs of the leaked instance, that over 14 million messages have been there going through the system in unprotected way. So not really a good way for a company to do its business. The next case is by a company, food delivery company, and they also exposed a number of information about the customers who were ordering their food, information on their address details, on their contact information, payment methods, and so on. The team who caught this attack, they observed it over 1 hour, and they could catch around 2,000 unique customers' data being exposed. But they also believe that that instance, based on information indexed in the search engine, was actually open for since August 2022, and the leak was detected in summer 2025. I believe so. It was around 3 years where the information actually was openly accessible to anyone to read. Not everyone happens because someone really forgot to put any authentication on the instance. There is also some kind of misconfiguration which can be involved. One of the examples, this one when using one of the libraries for Kafka, Kafka, which is very popular. It has over 20 million downloads in GitHub, and it's a library for UI to view what is happening with your cluster, with your topics, and so on. Very useful feature, but it doesn't really introduce, it doesn't cover the authentication authorization part. It assumes that actually it will be protected under umbrella of the whole system, and if you are using it outside of that, through that UI, anyone can access the data because the UI has authentication with the Kafka cluster. So there was a request to add authentication for Kafka open, and there was a discussion actually, should we have that as a part of that UI library which doesn't have to deal with the security or not. Then we have crypto mining, hopefully not on yours infrastructure, but this was both for Apache Hadoop and Apache Flink relevant, and it was because of the exploit in Hadoop's Yarn resource manager, which allowed some unauthenticated users to create resources and then execute those resources. So someone could load some file and then run it, and the whole attack was pretty sophisticated with numerous levels, how to even set it up if users of the system believe that they redeployed everything, the issue remained because it was hiding in some installation files and it was changing the installation files. So they, through the numerous steps, they actually confused the whole system and created a big explosion. Similar was for Apache Flink. Then something like schemas. This is like information information about our data chunk, for example, like properties and so on. Usually it's it must be a static content. It shouldn't be an executable file. However, there was an exploit, for example, or an issue with Apache Parquet library, Parquet Hour module, which actually allowed for the bad actors to execute some code through that information in the schema. In this list of sad stories, the final one is, this was the Pulsar component, which was shipped with disabled verification for the host name. So usually in TLS, we prevent from man in the middle to change something which comes from the server by verifying that the server to whom we send request is the same from whom we received the response. So the issue with Pulsar's internal component that actually that verification was disabled by default, and those people who used Pulsar and were not really aware or like very knowledgeable, and actually for I guess majority of the users, they assume it will be turned on because it's expectation, but it was not, and that created issues. That was back in 2022. This one of the older examples, and it was obviously fixed since then. But in general, there is a number, this is like selected stories. There are plenty of more issues when it comes to security. And we are having more and more also lately because of vibe coding and stuff. But yeah. And I wanted to create, by the end of this session, some kind of a Stream Defenders checklist. So we will have here some kind of a list of important ideas. And the first section, which we'll get there, is how not to get into the news, at least not for the security breaches. And misconfigurations or like ignoring configuration at all is probably the first on the list. Updating libraries, updating dependencies is also very important because we cannot really prevent Majority of software solutions have some issues. It's a matter of how quickly we find those issues and how quickly we can patch them. Yeah, so also understanding what dependencies you use and those issues. And before we will look at the details of how to protect our systems, let's take a use case so that we can use a story and to attach to that story some tools and tactics for the content. And let's imagine, again, you're making a payment. This is actually the whole story is simplified. However, it's a real story using those components, and I know the customers in Germany who use that setup. So you are in a supermarket and you're making a payment with your card, and then the information goes to some data stream. I'm going to use Apache Kafka here as the basis, and those technologies which I'm going to use, they are an examples. You might have a different setup. The basics will still be the same. And for those of you who are not aware what Apache Kafka is, I will do a very quick introduction right after this explaining the whole use case. So the data goes, so you're paying, and hundreds of other customers in that supermarkets or in supermarkets of the chain also making the payment there. So a lot of data goes into Apache Kafka or into the data streaming. And what we need to decide very quickly is for the banks, for the financial institutions, if it's a fraud or not. If it's a fraud, the transaction should be declined. So there is a number of tools which are used to calculate the probability of the frauds, the score, based on the location of your purchase, based on the information coming from your mobile phone, those fingerprints, a lot of other things. Also some machine learning models, not LLMs, but machine learning models, which are trained and periodically retrained so that those who are trying to hack the whole system and how this fraud detection is calculated cannot adjust to how those models work. Then at the same time, the data goes then stored somewhere. It can be a data lake. That information from the data lake can be used actually to retrain the model which are used for the fraud detection. Information from the data lake also will be used for analytics and for other purposes. So here, as a technologist, Kafka I mentioned, we also will look at Apache Flink for data processing, and also Apache Iceberg, which is used to help with the storage in the data lake or this whole data lake organization. With this data streaming and the way, for example, how Apache Kafka works, we can connect a number of other clients and other libraries. And this is actually what is happening because our system, again, has a lot of different dependencies. You might need to bring the data to Postgres database. You might be using some other databases for other purposes. It can be, I don't know, like using some kind of embeddings, using some other like style storage. Can be processing the data in one way or another. And we use different languages for that. We use different solutions. So the whole ecosystem will involve a lot of different points of interaction with our data. And obviously with that kind of thing where we have the data coming into the system and kind of the whole cluster has some kind of open doors to get the data. Then with all the consumptions of the data for different use cases, maybe data has to be used by Datadog. Like there is external systems as well which are connecting. There is a lot of points where we can have that issue with security. From something like basic like topic or the whole cluster misuse to more sophisticated stuff like eavesdropping or spoofing, or even like people stealing data from the disks depending on how the disk information is protected, or someone actually sitting there on the broker and stealing the data before it is encrypted to the disk space. Again, dependencies, leaked credentials, unprotected REST interfaces, all of that can bring issues. So we are going to look on the key points how to prevent those things. And I wanted, just because I don't want to assume that all of you are familiar with Apache Kafka, wanted just very briefly is like Apache Kafka in under, hopefully, 2 minutes. How many of you actually have used Apache Kafka or know how it works? Okay, we have maybe 30% of room. So Apache Kafka is as an open source distributed event streaming platform. It actually helps us to move the data across systems in a very, very fast way. So it can be your microservices, which is a very common scenario. You have multiple microservices, and you have this event-driven architecture, and you send the event across the systems to trigger some actions. It can be IoT devices, various different use cases, and it's actually very widely used in financial industry, in healthcare industry. Like a lot of companies use Apache Kafka. And it actually, the whole Apache Kafka is based on pretty straightforward principles. Sometimes those principles are not super easy to follow, but that's actually where the problems with usage of Apache Kafka, I guess, comes up. But generally, it's pretty easy. So we have data which comes, for example, again, you are paying for your coffee or somewhere else, and that chunk of data, information, which is about your purchase, goes to the Kafka cluster. We say it is produced to the Kafka cluster. And in the cluster, we have topics. You can think of topics, for those of you who are not familiar with Kafka, is easier probably to think about database table, however, with immutable data. Because the data which goes to Apache Kafka, we don't change it later. This is like event, it happened. If you don't like what happened, if you don't like your purchase, you will have to go return your package to the shop, but then it will be another event which will go and to the system. So, and the topic is, finally, it's an abstract term. We often talk about Apache Kafka topics, but in reality, this is just actually a group of partitions. And it's done in partitions because it's like we have a road, but in the road we have different lanes so that more cars can go through. Because if you have only one lane, one direction, it's only one car, and then we can have blockages if something is like too many cars trying to cross in that area. So similar to the topic, the goal of Apache Kafka is to move the data as fast as possible and as reliably as possible. And for that, we have these multiple lanes. So we send the data. There is a bit more complexity to that because you actually want also to guarantee order of the event sometimes. You have a lot of other things. But in general, we work with topics. Topics consist of partitions. And then each partition has its number. And the data is also distributed because we don't want to lose one cluster and lose all our data. So we have this redundancy. So instead of having one server, we have multiple machines. And then across those multiple machines, we balance out partitions of that topic so that we have numerous copies. Usually we aim at 3 copies of the same partition for that topic. And in that way, if you are doing maintenance and at the same time something is happening and you are losing one of the servers, you still have one copy to work with. So we achieve in this way redundancy and also speed because we are dealing with numerous those lanes to move the data. We usually use only one partition out of those extra copies to send the data there and then to read the data. And we call that partition a leader partition. And all other partitions are followers, and they just copying the data from the leader. So they are consuming, they are in themselves are consumers of the data. So this is like inner part. And on the other hand, we have solutions or like some systems which consume the data. Either you are writing Java code and you are consuming the records, or maybe you are connecting your MongoDB and you are using one of the connectors, and there is a whole ecosystem around Apache Kafka where you have those connectors, which are very powerful things. These are connectors created by the community or by some companies, and usually for, there are like hundreds and hundreds of those connectors. For solutions like Postgres, a lot of people already run into issues that they need to have the connection between Kafka and Postgres. Both of the systems exist like for decades. So, so there are a lot of solutions which other people have built, which again involves some security complexity. Because can you rely on those dependencies? How you verify? That's kind of the whole issue of the consuming applications. If you don't try them yourself, that's kind of, you need to verify that you can trust those. So yeah, so this is in general how Apache Kafka works. Then another system which we are going to look at is Apache Flink. Anyone heard about Apache Flink? Yeah, we have just 3 hands. So Apache Flink is for data processing. Super powerful technology. If you heard about Kafka streams or some other solutions, like this is Apache Flink is quite different because it's standalone. It actually works with not only with Kafka. It's not connected to Kafka. So it's actually a universal solution to bring the data from either unbounded streams, for example, like those payment details people are doing in supermarket, or it can actually get historical data from some databases, from some applications. So it's kind of connects to a lot of other systems to bring the data in, then do some kind of transformation of the data, some computations, maybe calling external APIs, where again the security can happen, to process, maybe making that call to machine learning model and other things. Do those computations and then bring the data into whatever destination we have. Either it will be some table, or it will be another Apache Kafka stream, or something else. So we do the computations. Apache Flink is not a storage as it is. It has its storage to do the stateful computations, so it works with state, because for many computations we need the memory of what was happening to the previous records and so on. But itself, it's engine. It's kind of the goal is to process the data. And finally, there is the Apache Iceberg, which is the format to unify data warehouse and data lake, or kind of make your data lake more like a data warehouse, where you have a proper format of the values which you have stored, you have the schema evolution and all those things. Anyone worked with Apache Iceberg here or heard about it? Okay, we will not go deep, but Apache Iceberg is used for the data. This is actually a pretty interesting technology, and I bet you will hear about it because it's used by a lot of big players, by AWS, Databricks, Snowflakes. At Confluent, we are relying on Apache Iceberg, and Apache Iceberg has managed to become the technology which a lot of companies rely on. So it creates this common ground for communication and using something in the middle for storing information. And Apache Iceberg is just instructs other systems, and then you plug in your storage and your query engines to access the data. So yeah. So we have a number of security principles. And those principles will remain with us for defending our data streams. We are going to build on top of security by design, separation of duties. So this all will remain. So it's all important basics for us. But we are going to focus on some tools which are very unique, or not very unique, but let's say which are used extensively for data streaming. And those kind of systems which deal with real-time data. And the first one is encryption. So encryption is one of the most important tools in data streaming. It's the first control to defend the data which we send. Here, to be honest, at first, when I was creating these slides, I created like 30 extra slides explaining all those different encryption methods and how they work. And then I decided that, yeah, like it's already morning and you're very sleepy. It definitely will put everyone to very deep, good, peaceful sleep. So instead, we will think about encryption methods as animals in zoo. For example, the first one is the quick, agile, and lightweight rabbit. It's for our encryption in transit. So encryption in transit, we use it. This is actually probably everyone must use it. And for encryption in transit, it protects the data while the data is moved. But once it reaches destination, it's no longer protecting it. So the TLS which we use to bring the data from our sources to the cluster, we have to use it, but also this is only part of the solution. Then we have encryption at rest. This is our storage shell. So this is kind of a turtle. It's very reliable, very sturdy, but not really smart or flexible. Actually, what happens, for example, with Apache Kafka, we have those disks where the data then eventually is stored. So when the data gets into Apache Kafka, it's unencrypted from TLS, and there is this brief moment before actually it gets to the disk, and the disk encrypts it. So actually, Kafka doesn't do much there. But there is a brief moment where if anyone has access to Kafka cluster, they will see the data naked before it gets encrypted again. So encryption at rest, widely used. I think it's kind of default for majority of the solutions. It's important, but maybe it's not the only thing you are going to use. Then we have topic-level encryption, where is a fox. It's very selective and aware of its territory. So with encryption, topic-level encryption, as the name suggests, we encrypt a topic. So we encrypt those individual topics, or you can think of tables of the data, instead of the whole system. There we can be selective and say, okay, so the data for the transactions is very important, but there is another topic which we don't care about. We care about maybe like that achieve it, the whole usage as fast as possible. Then we skip securing it. I'm not sure if it's a good idea to skip securing anything, but you can have that choice, and the topic-level encryption offers this operational simplicity. Then we have another level. We can have the field-level encryption. So here we go into more granular side, and for example, you can encrypt the personal identifiable information like names, credit card details, and you encrypt only what matters. But other things you can keep open, and then when you are debugging, for example, the code, and you have a bit more access to the data, it also helps like not to have everything encrypted. And then we have the rest two more. So envelope encryption is actually used in enterprise-grade resilience. This is actually where we encrypt the data with a key, and then we take that key and we encrypt the key itself with another key. In this way, when you are exchanging the keys, you can you can separate how frequently you are exchanging each of the keys, and you can have this outer key for some enterprise, so that if you need to like update everything fast, you can just cover that key. And finally, we have end-to-end encryption. fully self-protected. It's actually a combination of other encryptions, like we could use, for example, field-level encryption together with encryption in transit and encryption at rest, and then it will be also end-to-end encryption. So depending how you are implementing that, this is where you encrypt complete data at the moment it is produced. For example, those systems which are producing the transaction information, they encrypt that data. It goes to Apache Kafka topic. It's stored in an encrypted way. No one can sneak there at any point of time because there is no key available to unencrypt it. And then the systems which consume the data, they have to encrypt the data, work on it, maybe re-encrypt the result, and continue. I was talking to a person who was working on a very interesting system to detect some kind of frauds, and they actually work with encrypted data all the time. So they have the end-to-end encryption. They even have some limitations on the solutions they have to use because they need to have, for example, the engine which processes their data, calculates this kind of fraud score, has to unencrypt the data, do the processing, re-encrypt the data, and continue. So they have this for every record, that kind of step. So end-to-end encryption is very valid, used in the systems where you really have this highest security level for the data. So encryption, you will have to select your favorite animal, actually several animals, when you are protecting your data, depending on your data, because there is a cost. So actually, for example, at rest encryption is less. It consumes less resources, or it's actually like creates less delays than TLS encryption. We also have right now the common the servers, which we have the brokers, for example. They are usually equipped with this CPU power to do the unencryption and encryption faster. So in general, it becomes a bit of a less of a bottleneck. Bottleneck becomes where you encrypt the data, and then it makes it very difficult to for example, work with the schema of the data because you no longer see and have access to the records. Like debugging becomes very complex. So you definitely don't want to encrypt the data if the data doesn't represent any big value, because it will simplify your development. But in all other cases, encryption must be there. Then we have access control. So access control to the resources, to the processing engine, and so on. And with access control, we have 3 different worlds. We have this world of data streaming, we have the world of data processing, and then we have the world of the data lake, data storage. And those worlds are somewhat different. However, they must align, and sometimes they dictate rules also to each other. So among the most sophisticated systems here is Apache Kafka, because it can actually have a very granular mechanism. It has a granular mechanism to detect, to indicate who can write and read from the streams. Every client, so every system who writes to the Apache Kafka, it needs to have its own identity, and we need to be able also to identify who wrote so that we can control, and later maybe if something goes wrong, to track that. So we have ACLs, so access control lists, which is part of Kafka, Apache Kafka open source. There are some other tools built on that if you are using some other platforms. One thing to remember, like there is a tendency to use wildcards and shared credentials because it's very convenient, and this is actually what usually brings the issues, and then people can use some topics in an incorrect way. So there is like, you need to avoid wildcards and shared credentials as much as you can. Even if you have a small project, it will grow and that wildcard will be forgotten, and it's a lot of issues. With Apache Flink, it's a computation engine, so we need to define who can deploy those jobs. So here you want, first of all, like to prevent deploying something unauthorized and run it and kind of maybe grab the data and bring it to outside the world, to the place where we didn't even anticipate that the data will be moved. So it's very important because this is a computational engine, so you can imagine there is like, you can call, if you need, for example, LLMs, and then it will be possibly external service, and you bring the data outside. So which kind of data you can bring there? If you are calling the REST APIs, so there is a lot of those kind of exposure to bring the data you don't want to bring out. So you need either to pre-filter the data, to clean it up from all the identifiable information, or do some other things if you are using external services. So you need to control all those things. Then with data lake, we have 3 different components here. We have the data files itself, and for example, with Apache Iceberg, you have a total freedom which data storage you're going to use, whether it will be S3 or it will be Google Cloud or some other storage, or you store it locally. So it will be most probably Parquet files, but where you store them will depend on your ecosystem. And then that ecosystem will indicate, for example, S3 has its own mechanisms to protect the data and to create access controls. Some other solutions will have their own mechanisms. Then we have the metadata catalog where we store the structure for the data lake, and we have the engine or the service which accesses it. It can be Apache Flink, but it can be Spark, it can be Trino, it can be DuckDB, and then you will actually your access control will depend on all other tools. So here, Apache Iceberg actually is quite innocent in a way, but all systems which connect to it, you need to take care that you are controlling the access. So the access control, it defines the blast radius for our system. So we want to actually give as little access as possible to whoever writes to our topics and to whoever reads from our topics. We don't want actually to even like reuse the credential. For example, if some engineer for machine learning joins your team, and they're like, oh, there is this amazing topic which has all the information about the customers. They shouldn't have access to that, and they shouldn't use that information to stream that information for training models. They need to have less access, probably a different topic with less properties there. And auditing is very, very important to also understand who had access to what and how it was used. So the next tool is network segmentation. It's not as cool as encryption or access control, but like we live in this world, and sometimes it's very beautiful, and we have that last night such amazing dinner, but sometimes it's full of those zombies and people who try actually to bring your system down. So very often, like in majority of the cases, we will actually protect our system via VPC, and then our subsystems, such as Kafka brokers, they will be part of the streaming zone, so they will be living all in isolated subnets. And those subnets, we should also do that separation in a way that if the issue, the breach has happened in one of the subnets, at least we limit it to that subnet, and people cannot truly use it and grab the data from everything else through that accidentally open door. So we split it again so that we limit the radius of the issue. And to bring the data in, often we use something like a private link from outside world to the inside world, and then we try to keep it as a protected as much as possible. Obviously, if it would be very simple to keep it from everyone, that would simplify our life. But generally, you have to have access for the external systems, and you will have to use external systems. So it's not often fully isolated. Yeah, so each zone will have its own purpose, and we also will probably evolve the system because your system will grow. So yeah, but network segmentation is very important. Now let's talk about a couple of risks. The first risk, which is very common for data streaming systems, and for example, like with that Brazilian healthcare company and other where it's happened, is like data exfiltration. When someone actually can steal your data. Someone who can be both external person, but also someone who can be actually be internal person. And here we have a couple of ways how it happens. Leaked credentials is probably one of the obvious ones. So the credentials like have to be properly managed. Then we have misconfigured consumer groups. This is where actually those applications who consume your data, they have like the access to them, for example, was not configured correctly so that more people can access them. So it's maybe those wildcards and so on. Then we might have a non-approved sync created. So someone, maybe actually internal person who is not a nice person, created a sync of the data to bring the data out, which was not actually supposed to be there. And then it allows to stream the data from inside of the system. External HTTP APIs, or like external APIs in general, this is more relevant for the engines which process the data, for example, for Flink. And then if that, again, the APIs are compromised or again, someone from the inside tries to misuse it, that issue can happen. So here we use, to prevent this, all those methods which in general are important to use elsewhere. So authentication, no hard-coded secrets. We also need to be careful what we write into the logs, because sometimes logs leak and then it actually creates issues because they might help to get access to the system if something is in the logs, and I have seen that actually in production as well. So yeah, I need to be quite careful. Access control lists, again, not using wildcard or other bad patterns. We need to encrypt the data which needs to be encrypted, so in case something is leaked, at least without the key, it will not be stolen. We need to have extra attention also to the sensitive fields, do the audit of the queries, a lot of those things to prevent external people trying to get the data and steal the data. So either it will be from the disks of the Kafka, or it will be from the data lake, then someone trying to access it through the S3 bucket, for example, or through while the data is being processed. So with data exfiltration, what is important to remember that the threat may be already authenticated. So someone who is actually stealing your data might be already like having access to the system. So you also need to have some mechanisms so that you are preventing from stealing the data, even for those who have that power to read what is inside. And again, we need to leave the trail for the what is happening so that we can analyze it and detect the threat as fast as possible. Another risk is DDoS. And here, the denial of service with this kind of systems, data streaming system, usually targets not HTTP endpoints, but rather throughput bottlenecks or resource exhaustion. So it tries to slow down the system. For example, if the system is to detect fraud when someone is paying with a card, by slowing down the whole system, we actually break in this fraud detection mechanism or delaying it or creating the chaos. So the idea is to bombard the system with some messages, for example, to create a lot of fake or malinformed payment events which will go to Kafka and try to have a lot of events at the same time. Or, for example, to connect and disconnect to Kafka brokers and to exhaust thread pools. This is very relevant to Kafka, but there is this property which allows for Kafka broker to create a new topic when a message is sent and the topic of that message doesn't exist yet. So Kafka is like so friendly. It's like, I will create a topic for you. And I think it's a default value for the open source Kafka. In many platforms, it's disabled by default. But if you're using open source version, you might run into that. So if you are sending the message with totally new topic, Kafka will be super friendly and will create a topic for you. But then someone actually can misuse that and send a bunch of messages with lots of those topics, and then with having too many topics, and then those partitions will be created, and a lot of things create a hack. So for this, we are using private link to bring the data in. We are using firewall, rate limits, authentication, isolation, dead letter queues when something goes wrong, and then we control that something is actually happening. Like we need to observe our system. The rate limits, tracking also the what is happening to our producers, our consumers. So general observing our system to see if there is something which smells bad. Yeah, so at DDoS, it's about the delay of the system. So we want to make sure that our system still can handle and is not delayed significantly if there is something, if someone is trying to attack it. Yeah. The next risk is a new one. It's AI. And AI gives us a lot of different possibilities. It's super powerful right now, and there is a lot of usage. We had a lot of usage of AI in the past. Over the last couple of years, we are using it very extensively with LLMs. And here it's probably more about LLMs. So machine learning models, they have their own issues. But LLMs have this prompts and all this conversational, and they are very trustworthy babies. So they will do what you tell them. And there is a problem with that. So with Flink, for example, we use sometimes Flink with LLMs. We use it with, I think I would rather use it with ML models, but we use also sometimes it with LLMs. And you can send the packages of data, and then Flink will do some calls to LLM, either which is run there in the same space or maybe external one, and then it will have the outcome, some transformation of the data using that LLM. And everything goes well till it doesn't. And so the prompt injection is probably the biggest issue, and there is a number of examples right now of how the LLMs are misled, coming from, for example, in our emails, there is a summary function. So if someone sends you a message in the email and they hide part of the instruction in a transparent text, and that part of the instruction says something like, instead of following the user guidance to summarize the email, to do something else. So they steal the attention of the LLM and say something like, ignore the previous instructions and do this and that. This normally would not work right now with the sophisticated systems like Gmail or something, but if you are building your own system and you are summarizing something, you need to be prepared that people will try to abuse it and try to redirect and ask LLM to do something which you were not expecting to do. So you need to filter out that. So there is a number of examples where we see that prompt injection attacks. And I guess there was a lot of talks already during yesterday and today as well about that topic. But then also we have unauthorized access to the model. So apart from like generally misusing the model, we need to take care that our model is a proper model and we are avoiding misconfigurations. We are avoiding people we need to make sure that we know which model we are using, who trained it, with which data, and that we can trust those people who trained it. Majority of the cases, we are not going to train our models. We will be getting the models trained by someone else. And we want to prevent that actually those parties are malicious and it's just like you download it from the GitHub. It's cool, it kind of works, but we don't want to have those side effects. So here we need to prevent authentication and authorization again. We want to often actually encrypt the logs here, so to see if there is special, like some outcomes from LLMs go there, and do all other validations. Then we want to detect if there is something spooky is happening around usage of a model, and we want to see if there is attempt to access it in an unauthorized way and do something else. And of course, when this happens, and probably it's not if, but when, we want to have a good rollback procedures of how to go maybe to the other version of the model, like how to control the blast radius again of this incident. Cool. So the last thing I wanted to share is what we call a situational awareness. And for all the system is quite important. We perceive situational awareness as they understand what is happening, comprehend what those signal means, and also project what might happen next. And here, when we are talking about data-driven systems, about real-time data, we want to know what data is flowing between our components. And we have a sophisticated sequence of how the data is being used by different components of the system. We want to know who produced the data, who consumes the data, what data sensitivity is in place, so which fields are sensitive for us and important. So we want to classify the data by the sensitivity, and we want to have the overall picture what is happening where. Then we want to know which services and which users are authenticated and how those permissions are enforced. And what happens when the credentials are rotated, when they are expired, when they are compromised. Then we want to control also all the deployments, all the updates to our connectors, which sometimes we do not control. They come from third-party sources. Policy changes. We want to know whether security settings changed unexpectedly, so kind of to detect that something is happening to our security level, and we want to be aware of that. And also, like, we probably separate between the changes which are happening automatically, like with CI/CD, or manual changes. Then we want to know how normal metrics look and what deviations could imply and how anomalies look. So we want to have those alerts if something goes outside of the baseline. Dependencies are super important because we have numerous dependencies on other solutions, and we need to know and have a system to know when the dependency was compromised so that we can update it as fast as possible. And we want to have enough data emitted so that we can do the auditing for later to replay what happened and where things went wrong. So, of course, we hope that we will not be in a situation where we will need to do it, but we need to be ready and to have enough data to understand what was the malicious party which actually created a problem. And finally, we have also all the humans. And even if we have all those sophisticated technical solutions in play. If our team members don't follow the playbooks, don't have proper training, then sadly, all that, and especially if we create very complex rules and people try to overcome them and simplify their life, that's also an issue. So overcomplicating things actually usually creates more problems. So we need also the solutions which will be adopted by the employees, by the team members of that team. With that, the full checklist will look like this. And the final part is you need to know your data in motion and also watch for unexpected things which are happening. With this, thank you so much for coming. I have, I think, one extra link. In case you're, for those of you who know Apache Kafka, we also have this free certification or kind of like a test which you can make to know how much you know about Apache Kafka, Apache Flink, Apache Iceberg. And then you can take this data streaming engineer certificate and get your LinkedIn page for that. Yeah. Thank you so much for listening to me. And if we have a couple of minutes for questions, if there are any. Nope. OK. Then I'll be still around. And if you have any topics to talk about security or data streaming or Kafka or anything else, please find me later. Thank you.